All right, here we go. So if you take a look at this, you might be able to see your house, or you might even be able to see us. Like, I'm looking right here. Look, there we are. Okay? This is a satellite view of Syracuse. So one of the questions I'm going to ask you is, how far is it from the high school to Glen Eagle Golf Course? So think about that for a second. One of the things you might be asking yourself is, oh, well, I don't know how long those roads are, okay? So I went ahead and looked up online here, and according to Google Maps, they're each 1.2 miles from that intersection where the Walmart is, okay? So they're each 1.2 miles away from that intersection. So you could say, oh, well, if it's 1.2 miles away on both sides, then isn't it just 2.4 miles away? Let me pose another question. If I had a hoverboard, okay, and I wanted to go straight from the golf course to the high school or follow that purple line, how long would it be? So go ahead, pause the video, take a moment, and try and figure out how long that would be. Okay, after you've thought about it for a second, so remember, we got 1.2 miles here and 1.2 miles here. Well, this is a right angle, okay? And last year we were introduced to Pythagorean's theorem, okay? So Pythagoras found out if there is a right angle, we can use both of the legs, square them and add them together, and that equals the hypotenuse squared, okay? So both of the green lengths are going to be A and B. So I have 1.2 squared, and I add that to 1.2 squared, and I'm going to figure out what the length of the purple line squared is, okay? So we're going to need our calculators, so we pull those out. So I get 1.44 plus 1.44 equals c squared. I add those together. We get 2.88 equals c squared. Now again, how do we get c by itself if it's being squared? Let's review from last year. Let's see how fresh in our brain it is, okay? So we have things called inverse operations, like multiplication is the inverse of division and vice versa. Addition is the inverse of subtraction, vice versa. So we have the, if we're squaring something, the inverse of that is actually the square root, okay? So we're going to take the square root of both sides. So we get c is going to be the square root of 288. Now on your calculator, if you hit the second button, right above x squared, you see the little square root symbol. Hit that, and then we type in 288, and we get, and we're going to round here, 1.697 miles, okay? So now we think about it. Would it be quicker to just walk down the street to the intersection than over to, so like, is it quicker to leave Glen Eagle Golf Course, walk to this intersection, and then that's a terribly straight line, okay? That distance is 2.4 miles, both the green lines added together, and the purple line is 1.697 miles, okay? So that's just a refresher from last year with Pythagorean's theorem. Okay, so this, remember it, is another Pythagorean theorem question. So we're trying to figure out what the length of that guy is. So I've got 3 squared. I add that to the unknown squared, and that's going to equal 6 squared. Okay, I know 3 squared is 9. I know 6 squared is 36. To get the x squared by itself, we're going to subtract 9 from both sides. 36 minus 9 is 27. Okay? All right. To get the x by itself, we take the square root of both sides. I get x equals the square root of 27. Now, we did do this a little bit last year, and we're going to need a refresher eventually. But if I wanted to simplify the square root of 27, simplify that radical, I need to find the prime factorization of 27. So I ask myself, what's the smallest prime number that goes into 27? 2 doesn't, but 3 does. Goes into it 9 times. Okay, 3 is a prime number. Is 9 a prime number? Nope. 3 goes into it 3 times. Those are both prime numbers. Okay. Since I am taking the square root, I'm looking for pairs of numbers. I got a pair of 3s, so I can pull out 1, 3. And then what's left underneath the radical? Just 1, 3. So the length of x is 3 square roots of 3. Okay. Graphing the function here, -1. My y-intercept, and I'm going up 2 over 3. And now I can graph my line. Okay. All right, go to 6.1 in your Spider-Man book. So what we're going to do is introduce something called, well, you should have talked about it last year, but translations, rotations, and reflections. Okay. All of these are called transformations. They take something on a graph, on a two-dimensional plane, and they transform it. Okay. We're going to talk about some tools and strategies we can use to translate, rotate, and reflect a figure. So yeah. So the joke is, I wanted to buy a pair of camouflage pants, but I couldn't find any because you can't see them. Oh yeah, what's the deal with pink camo? Anybody ever thought of that? Anyways, here we go. So what I want you to do is look at this. And one of the things we're going to do, we're going to take point A and we're going to reflect it over the x-axis. Okay, so we're going to flip it over the x-axis. So what's going to happen is point A, when we reflect it over the x-axis, its new location is going to be right here. If you notice, here it's 2 away from the x-axis, and here it's also 2 away from the x-axis, okay? So that's a reflection over the x-axis. Now we're going to reflect it over the, so after you reflect, or after you perform a transformation on a point or on a line or something, so especially a point, so the pre-image, or where it originally started, is A, and after the transformation has happened to it, we're going to call it A prime. So that little apostrophe is after we've moved it, okay? So now let's try reflecting it over the y-axis. So here we go. A is 5 units from the y-axis on the right side, so it's also going to be 5 units away from the y-axis on the left side. Okay, so that's reflected over the y-axis. Ooh, here's a good one. What about rotating it 180 degrees counterclockwise around the origin? So if we went 90 degrees counterclockwise, its new location would be right here. Okay, that's 90 degrees counterclockwise. Basically, one way you can do this too is with patty paper, but I haven't handed any out to you. Okay, so there's A prime, so that's after it's rotated 90 degrees. And we're kind of just, we haven't learned any of the rules yet, so we're kind of just eyeballing it, okay? Now, if it's asking me to go 180 degrees, so I'm going to go 90 more. So 90 more degrees counterclockwise is going to put A prime right there. So there is A prime, okay? So that's A being rotated 180 degrees counterclockwise. And you can also ask, isn't that the same as 180 clockwise? Sure is. Okay. All right, let's do one more. Or 2 more, I guess. One more rotation, though. We're going to rotate it 90 degrees clockwise. Oh, I didn't even go counterclockwise. We went clockwise that last time. Oh my goodness. Learn to read a clock. Jeez. 90 degrees clockwise puts it here. Okay. So this is for D. 90 degrees clockwise puts it there. Now if I go back to C, because I know how to read a clock, 90 degrees counterclockwise would put it there. So 180 degrees counterclockwise puts it there. Good grief. Man. Let's talk about clocks for a second. This is clockwise. Okay? This is counterclockwise. Okay, we're good. All right. Let's take A and translate it left 2 units and up 3. So left 2, up 3. Puts it right there. Okay? So those are the different transformations we're going to be using here in a second. So in animated films, they actually do use transformations, okay? So they're now usually produced using computer technology rather than the hand-drawn images used in the past. Computer animation requires both artistic talent and mathematical knowledge. Sometimes animators want to move an image around the computer screen without distorting the size and shape of the image in any way. This is done using geometric transformations, such as, so in your book, there's a spot for vocabulary. I want you to write down these 3 vocab words: translation, reflection, and rotation, okay? To help you remember what those actually are, or what those are, next to translation, you can write a slide, so it slides. Next to reflection, you can write flips. And next to rotation, you can write turns, okay? So they use those geometric transformations. Sometimes they use one, sometimes they use a combination of all 3, okay? These transformations need to be precisely defined so there's no doubt where the final image will end up on the screen. So today you will be animating the lizard shown on your handout. So you should have gotten a handout in class. If not, it is uploaded to the Canvas page. You can print one out. And we're going to be transforming that lizard in various ways. So here's the lizard. It has its anchor points, okay? So if you wanted, you could label all these points, like this is point A, this is point B, this is point C, and D, and E, and so on, okay? So when, like, the anchor point A goes to a new location, you could call that new location A prime, okay, with a little apostrophe. Or you could call the new location of B, B prime, okay? All right, lazy lizard, what you're going to do, this lizard wants to translate this I can read, hang on. We're going to translate the original lizard so that the point at the tip of its nose is located at 2420. Remember, this is our X, this is our Y. We want this lizard to look like it's sunbathing on that rock. This right here is a rock, not a potato, okay? So go ahead, give that a shot. Rotate those, or translate all those points so it looks like he is sitting on that rock sunbathing, okay? Now, so that handout has multiple illustrations of this scene, right, of this lizard. Now what you're going to do is you're going to rotate this lizard 90 degrees about the point 12.7 so that it looks like the lizard is diving into the puddle of mud. Now, remember, we know how to read a clock. So, 90 degrees, so it looks like he's diving. It doesn't say here. So if he's diving, his body needs to be facing downwards, right? Okay? So if he's rotating 90 degrees, and I'm assuming he's rotating 90 degrees this way, excuse me, and on a clock, that is counterclockwise, okay? So we're going to rotate 90 degrees counterclockwise. That's a terrible K. That is even worse. Okay? So go ahead and give that one a try. Now, this lizard is going to be jumping. It's going to be leaping. Okay? So there's this line up here that goes right through the cactus. He is going to be reflected over that, so it looks like he's doing a backflip over the cactus. Okay? So go ahead, give that one a try. All right. So make sure, or we said vocab, make sure you have some sort of a definition written down for these three terms in your book. Okay? Again, make sure you take the time to try all three of those examples with the lizard. Okay? I will post an example of what it should look like when you're all said and done. Okay? Now, just writing down what I did is not going to be helpful if you don't know how to do it. Okay? So, you are more than welcome to work with the people at your table, or if you're watching this at home and you weren't in class, you can come talk to me. You can talk to your classmates when you are in class during other prove it time, okay? Just writing down the answers is not going to help you if you don't know how to do it. Okay, this is a big word, congruent. Two triangles are congruent if they are the same size and same shape. We're going to get more into congruency theorems later, but just have that word in the back of your mind. It doesn't mean the same thing as equal, because if I say two triangles are congruent, I'm not saying they're equal because they're not the same. Or they're not the exact same triangle. They're two different triangles. They're just congruent. Okay? Pre-image and image. So the pre-image is before a transformation has happened to it, and the image is afterwards. So if you notice, like, here's B is circled. That's the pre-image. B prime is after one transformation, and B double prime is after a second. We will learn more about these next year. Okay. Reflection. Okay. That's when it flips. That's another word we use was flip. Okay. Rigid transformations. So transformations are the translations, rotations, and reflections. Okay. You take a polygon or an image or something, and you perform a transformation on it. Rotation is about a specific point. Last year we should have done some of these where they were about the origin. Today they're going to be about a specific point. The one with the lizard rotating so it looks like he's diving. That was about a specific point. Then translations, where things are shifting around on a two-dimensional plane. So go ahead, try to prove it. Again, do not just write down the right answers. It will not help you if you just write down the answers. Okay? We are less worried about you knowing how to get the right answer, and we are more worried about the how you got the right answer. Okay?